Elon Musk je považován za pionýra v dobývání vesmíru a oproti spoustě jeho jiným nálepkám je tahleta určitě oprávněná. Je tady ale celá řada lidí, kteří se o posouvání hranic našich možností zasloužila minimálně stejně jako on, ale nevíme toho o nich tolik, protože nemají kolem sebe tak velký hype a PR, protože to možná ani nechtějí. Každopádně mým dnešním hostem je jeden z těch lidí. Člověk, který byl hlavním architektem vesmírné lodi New Shepard, vesmírné lodi společnosti Blue Origin, která v ní už několik let velmi úspěšně a bezpečně vozí turisty na nízkou oběžnou dráhu a zpátky. A která samozřejmě patří Jeffu Bezosovi, majiteli Amazonu. Vítejte u dnešního podcastu, já jsem Cíp, díky všem za podporu tady na YouTube, streamu a hlavně pak na Hero Hero. So, and my guest is the former chief architect of New Shepard, the Blue Origin rocket, of course the space startup of Jeff Bezos, and now the CTO of Interlune, a startup focused on bringing rare resources from the moon back to Earth. Mr. Gary Lai, hello and welcome.
Thank you. I'm glad to be here.
I'm sorry, but I have to ask you the question you already heard like a million times. You are one of the few lucky. You've been out there in space. How was the experience? And was there for you some kind of realization moment or something you realized looking down to the Earth, like we are so insignificant like humankind or something like that?
Well, the experience for me was very personal and it was very overwhelming. And that was kind of surprising because I was approaching the mission, having led the design of the New Shepard rocket, trying to think about the experience and how it compared with what we intended. I'm one of the rare and maybe the only lead designer of a spacecraft, of a rocket that has actually flown it to space themselves. But for me, the second the engine lit and we took off, I really couldn't think anything about anything. I was so overwhelmed by all the sensations and the experience that I did not have an intelligent thought in my head the entire time. It was just a complete primal, visceral experience. But I could still recall it very, very clearly, even to this day, and it's been over 3 years. I think the thing that surprised me, not that I had an aha moment, as many people sometimes say when they see the Earth from space. But I was very surprised by when I looked out the window that most of what I could see was just the blackness of space. And I had to actually look straight down through the window in order to see the Earth. So it did speak to me a bit about the insignificance of Earth in the grand cosmos and how precious it is.
Mm-hmm. There was quite a brief moment, like 3.5 minutes. Mm-hmm. Why is it so short time with the rocket, with the Shepard?
Yeah, New Shepard is a suborbital rocket. So in order to spend a long time in space, you have to get into orbit. You have to not only go up, but you have to start going sideways very, very fast so that as you fall, the Earth is falling at the same speed with you. So you basically fall around the Earth. New Shepard goes straight up and comes straight back down. And without that time, gravity will very quickly grab the spacecraft. And without that speed, gravity will grab the spacecraft and bring it back down very, very soon. If it was much longer than 3.5 minutes going up, we would not be able to survive the re-entry accelerations of just hitting the Earth, the atmosphere that quickly.
Okay, so how far the rocket goes, or the capsule?
About 107 kilometers up.
So everything above would be not safe for the people?
Yes, even going 107 kilometers up, when you hit the atmosphere is only about, the thick atmosphere is only about 10 to 15 kilometers thick. So it's almost like dropping a pebble into a pond. When you hit it very hard. And so when you go up 107 kilometers and come straight back down, you have about 5 to 6 times the acceleration of gravity that you experience when you hit the atmosphere. And the higher up you go, the higher that acceleration you'll feel when you hit the atmosphere.
Mm. How many people are in the capsule?
There is 6 people in the capsule.
How did you design it?
Well, we wanted everyone to have the same experience. in the capsule. So every seat had to be a window seat. So in order to have that same experience, we arrange everyone in a circle around the capsule and leave room for the hatch in the seventh place. And people need to be a little bit reclined. They cannot sit straight up, because when you hit the atmosphere that hard, if you are not laying on your back a little bit, the blood will just push down away from your brain and you will actually black out. So having 6 people reclined in the capsule, it tells you how big it needs to be. And that was about the biggest capsule that we could transport easily over the road. So that's how 6 came about.
Okay. You said it's not usual that the designers and the architects of the spacecraft are in there. How come?
I mean, in the past, most people that have flown to space, really up until very recently, are professional astronauts, very often test pilots, and then afterward that scientists. And they undergo years of training. Typically, an astronaut from NASA will go through 2 years of training before the first space flight. And so this is not something that engineers or people that design the rocket can devote the time to. But we designed New Shepard to be able to fly anybody, even people that have disabilities or people of advanced age. The oldest person that's flown on New Shepard is 90 years old. And so anyone, including myself, could fly it. And I am not a test pilot. I'm just a normal engineer. I had, in fact, never experienced weightlessness or that high of acceleration before the first time I flew.
But you shouldn't be on that rocket at that day. Is it right? You substitute for Pete Davidson, I've heard or I've read somewhere.
Yes, Pete Davidson, the comedian. He was going to fly, and then he had the last minute drop out. And so I had been told, because I had led the project, that they wanted to give me the opportunity to fly it someday, but I would have a standby seat because, of course, the seats are very valuable. We don't talk about the price, but they are very high, at least until in the future when they will come down. So that opportunity arose really 1 week before the flight. I was told there was an opportunity. Did I want to take it? And if so, I would need to pack my bags and get to Texas.
How much you hesitate?
I didn't hesitate at all. I had already known that if there was an opportunity, I would take it.
You were the chief architect of the Blue Shepard, New Shepard, sorry. What actually was your role in the design of the whole thing, or right. Some key thing in there?
Yeah, so when we talk about architecture and space vehicles, it's actually not that different than an architect of a building versus an engineer of a building. An architect of a building will figure out what the building looks like, how the spaces will be used, how people will move through the spaces. But in order to actually build the building, you also need engineers, which will determine how and make sure that it stands straight, that you can get water through the building, that you can get electricity through the building. So the engineer is not the person that tells you what the building will look like. The architect is. And the architect needs to know enough about engineering in order to make sure it can be built. In a spacecraft or an airplane, the architect is the person that comes up with a high-level solution and then works with a team of engineers in order to actually build it, in order to design it. The engineers are usually very specialized. You'll have mechanical engineers, very special engineers to do the rocket engines or the fluid systems or the electrical engineering or the software. They will each have their own specialty. As an architect, I need to know a little bit about every single one of those disciplines so I can design the entire system. And of course, it's not just me. New Shepard was designed by over 150 engineers on staff, including the system architecture group, and I led that entire group.
What was the hardest part of designing? I can imagine all of it, but if you look at the process, what was the toughest?
I mean, you have to take a step back and think about where New Shepard was when it started. We started the program in 2004, and this was well before the time that rockets were reused. New Shepard was the very first rocket system that was ever reused that could demonstrate that that was possible. And around 2004, about 2% of everyone that had ever flown to space died in the process, either go on the way up or on the way down. So we had this challenge that we wanted to design a system that was so safe that you can actually have tourists fly on it. And they're not going to want to risk their lives at all. And then also because they were tourists, you have to make it very inexpensive. And by very inexpensive, it has to be very simple to operate and very, very reusable. Neither of those two things, the safety or the reusability, were demonstrated at all by the time we started, in 2004. So coming up with that complete system and then actually testing it well enough until we were comfortable flying people on it, and then they were comfortable, the customers, of which there are now many, many customers, a long backlog of customers, are confident enough in the system. There were many challenges.
What was your approach for the reusable of the rockets?
Yes, so as a system architect, we actually started with very, very few preconceived ideas of what New Shepard would be. You could actually fit the objectives or the requirements that we were given by Jeff Bezos on one paragraph.
That was it.
It was it. He's wanted to get people into space for tourism. He wanted to give them a very nice view. He wanted to be very inexpensive. He did talk about a dollar amount, which we can't talk about, but there was an objective. And everything else we had to figure out. And that's the job of an architect. That was my job in order to, from that very simple description of things that we wanted,
how much time did you get for this goals?
Well, it took a long time. We started the project in 2004, and by the middle of 2004, by the end of 2004, we had a general idea that we would have this capsule that would separate. We would have a booster that would restart its engines and land vertically. When we started, we didn't know whether the vehicle would have wings or not. We didn't know that there would be a separate capsule with parachutes. We didn't know the propellants. The types of rocket engines didn't exist. So we in about 6 months, we came up with the very high-level concept and then started designing and iterating and making many versions over time. And it was not until 2015 that we landed the rocket for the first time successfully. So it took a while.
And did you count that will take so long?
No.
Where was the origin goal?
The original goal was to start flying it within about 5 years, and we did reach that goal. In about 5 years, we flew the first version. And in about 6 years, we flew the capsule for the first time. But that was just the beginning. Right? We went through many, many, many tests, many flights, many versions before we were comfortable flying people. In fact, the very first time people flew on New Shepard was the 16th flight. And by then, we were 4 different versions of the vehicle had already come and went.
How much your ideas matching the reality in the process?
Where we started was very difficult very different from where we ended. We actually started with totally different propellants. We started with a very different concept for the capsule. In the beginning, we actually thought we would have there would be no capsule, that there would be a single rocket ship and you would simply land on it and no one there wouldn't even be an escape system necessarily. But we quickly moved away from that idea because we knew it would take time. And so this is the tension between having a system that is very simple and low cost, which would be no separating capsule, and the emphasis on safety, which we realized until we perfected vertical landing, we needed a separate capsule that could escape at any time.
How do you perfect something like that, like vertical landing? It's quite unusual to see such big object to land like this.
Yes, it's very unusual. In fact, in 2015, when we did it for the first time, no one had ever done that before. And so it took a lot of simulation, it took a lot of engineering and math, and it took a lot of tests that we could do without trying it for the first time. And in fact, the very first time we attempted it on the first New Shepard mission, it didn't work. The vehicle crashed on that first mission. So several months later, we built another vehicle, and we were able to do it on the second try. And it's very exciting, actually. Tonight, as we're recording this, the much bigger Blue Origin vehicle, the New Glenn rocket, which is designed for orbit, will go on its second mission and will attempt to land on the second try, like New Shepard did.
Yeah, but New Shepard is like 18 meters long, and the New Glenn is like 90 plus meters long.
Yes.
Is it right?
New Glenn is 38 times the thrust of New Shepard. It's actually so big that you could put the entire New Shepard rocket in the payload bay of New Glenn and launch it to space.
Okay. When you were in the Blue Origin, you designed just the New Shepard, or
I worked on every program at New Shepard.
So New Glenn as well.
Blue Origin. Sorry, I worked on every program at Blue Origin at one point, including the lunar lander programs. So I actually worked on New Glenn, the very early versions of New Glenn, in between different times I was assigned on New Shepard. And I was also the design review chair, which means the person that inspects and passes the design for the lunar lander program for Blue Origin.
Okay, so New Glenn is one of your child as well.
Yes,
you're
a
proud.
lot of people have a stake in it, but I was there from nearly the very beginning.
Okay, what were the other problematic parts of designing New Shepard? Like the capsule separated from the rocket itself. How the mechanism of pushing up the capsule is working actually.
Yeah, the very hardest part of designing any space capsule is the ability to escape. So that is the capability that if something goes wrong on the rocket and it starts to go out of control or it explodes, that any second, at any instant, the capsule has its own rocket system, and it can push itself away. And that starts from on the ground. If there's a problem on the ground and the rocket is about to blow up, you have to be able to escape. Or you are in space and the rocket is about to cut off its engine, but something happens the last second. And then the hardest part, which is right in the middle when you're going supersonic, and the drag is pushing the capsule back onto the rocket, and it doesn't want to actually separate. At that time, you also need to escape. Designing that system and designing it in a way that was reusable was very hard. No one had ever done that before. In the early days of spaceflight, such as with Soyuz or Apollo, they have these giant towers that stand on top of the capsule, and if there is a need to escape, they actually pull the capsule off the rocket. But you can't, that is not reusable. That tower must come off every time. So we needed to design an escape system that was actually embedded inside the capsule, and that if we didn't need it, we would land with it and we can reuse it again and again and again. So that was a brand new concept, and it needed to be tested.
And how the system works? Could you tell me?
Sure, I can tell you a little bit about it. So it is autonomous, so it is monitoring for something going wrong on the rocket. And if it detects, it's watching every 10 milliseconds for something to trigger, and then it will count multiple 10 millisecond times. And once it passes several consecutive times that it seems that something is seriously wrong, it will start the escape system. So the entire time between something being detected that is wrong and that the time the escape motor is firing to get the capsule away from the rocket is 130 milliseconds. It's actually about the blink of an eye. That's how quickly it has to work. And because of that, these systems really cannot be piloted by human beings. A human being cannot react that fast. Or if they could react that fast, they would be too prone to making a mistake. Mm-hmm. And so what happens is the motor fires. There are explosives that blow the capsule off the rocket very quickly, and the rocket fires until it has a system which tilts the exhaust and moves it not only away but to the side of the rocket. In case the rocket is still thrusting, it basically will bypass the capsule. And then parachutes come out and you bring the capsule and the people safely to the ground. And we have tested this many times.
And one time it's actually deployed before the line that shoot, right?
Yes, on the 23rd mission of New Shepard, we were having a payload flight, which means there were no people on it. The capsule was filled with scientific experiments, and there was a problem on the booster, and it started to go out of control. Then part of the nozzle actually fell off, and so it started tilting. And the second it tilted only about 10 degrees, the escape system realized there was something wrong and rocketed off. It was completely unplanned. It worked perfectly, and the capsule was recovered, and all the experiments were intact.
So you were happy that it happened like it should?
I was happy it happened, and I was also very interested to look at the data because although in a test there is a lot of data, but you sort of know what to expect. Because you're planning to test. This is the first time actually in history of spaceflight that you had an in-flight escape that was completely unplanned and the escape system went off. And so that we wanted to see how well it worked in a real-life situation, and it worked perfectly.
How many rockets you destroyed in the process?
In the previous tests, we actually didn't destroy any rockets. In fact, we expected them to be destroyed, but the New Shepard booster is so powerful, so robust, that in the one test that we did, where we needed to escape at supersonic speeds, the booster actually survived. The rocket survived.
There are windows in the capsule. How did you come up with that idea? And they are quite big.
They are quite big. One of the requirements that we had in this very short list of requirements is that the windows had to be very big. In fact, the idea was that someone sitting in the capsule would have the impression that they were floating in space because the windows would be so big. And that is the experience you get in a New Shepard capsule when you are seated and you turn your head. The window is so big that you cannot even see anything out of your periphery vision except the window. And when you look across the capsule, most of the view is dominated by the windows. This is obviously a very hard engineering problem to make a window
survive
that large, survive, and it's actually redundant. It has multiple panes and it has multiple seals around the window
and
as
how
well.
Thick they are?
They're quite thick. Can't go into the exact details, but they're very thick. But still, the clarity is incredible.
If you look to the space race we are right now, because there is a lot of going on in the space region, in what kind of era we are right now?
We're just at the very beginning. We're not quite at where the Wright brothers were for airplanes, but we were clearly in the barnstorming days, the kind of days of early aviation, the pioneers. We're only getting started, but it has really been incredible how much progress there has been in the last about 10 years since New Shepard successfully landed. Shortly after that, SpaceX landed the Falcon 9, which is obviously a much bigger rocket, and they have done that now over 500 times since then. They have recovered Falcon 9 rockets, and they are now working on the Starship, much, much bigger rocket, the biggest one ever flown. Blue Origin is working on New Glenn. And there are other companies. You don't hear much about them, but some of them will succeed, including ones not just in the United States, but in China and in Europe that are now in this race. So it is a race on many fronts. And different from a race, a traditional race, there will not be only one winner. This market is big enough for many winners, just like there is more than one company that makes airplanes. There will be more than one company that builds reusable rockets. And they will be flown all the time, every day.
Is there space for that?
There is space for that. In fact, it is growing so quickly I believe I heard a statistic that even though the first space launch happened in 1957, so a very long time ago now, more than half of all the satellites launched to space in history have been launched in the last 5 years. Yeah. So it is growing exponentially. Now, in literally almost every single day, there is a space launch. I think it's close to over 200, 250 space launches per year right now and continuing to grow. So it will not be long before it is every day.
Why should we be interested in space so much?
Space is an incredible economic opportunity, and I think ultimately will also be an imperative. There are many things that we already depend on space for in our everyday lives. Satellites are used in all modern industries. If you watch the weather forecast, if you navigated with your phone with GPS, if you made a telephone call, a lot of the times the traffic or internet is routed over telecommunications. Defense industries obviously use satellites all the time for reconnaissance, for watching out for nuclear missile launches. There's just endless numbers of uses, even today and in the past, for satellites. And now with the cost of launch coming down so quickly because rockets are finally being reused, over the course of my career, the price of launch has gone down by a factor of 10. And in the next 10 years, I believe it will go down by yet another factor of 10, so about 100 times. You can now think about applications such as putting large data centers in space, or what we work on in Interlune, which is utilizing the natural resources of space, actually mining the moon, mining asteroids, and bringing those resources back to Earth. Because the solar system has abundant resources. We obviously have many natural resource problems on Earth. It is often the source of war. There is an abundance of resources in space. In many cases, thousands of times more natural resources in our solar system than on Earth.
Shouldn't we pick up our mess in the Earth at the first place before we entering the space and make a little bit mess there?
Well, I would rather see that a mess is being made off the Earth than a mess is being made on Earth. Certainly, we need to pursue conservation efforts. We need to take care of our planet. But I believe an important part of that solution in the long run, not necessarily today, but certainly within my lifetime and the lifetime of my children, is to utilize the resources of outer space, again, which are in so much greater abundance and with so little environmental impact on Earth resources, that once the cost of space launch becomes low enough, it's imperative that we pursue that solution.
You are pursuing quite interesting solution for the mining or the getting resources from the moon. Actually, that's a Helium-3. What's the case? What are you doing right now?
We have to start somewhere. And so Interlune, the company that I co-founded, we want to be a natural resources company where we're bringing resources back from space for use on Earth, as well as in space to grow an in-space economy. I think that in the long term, the in-space economy, one where resources are used in space for the purposes of staying in space, to live off the land, that is ultimately the larger growth area. But to get started, we are starting with a resource called Helium-3, which is the one resource that is relatively abundant in space, particularly on the moon. It is very, very rare on Earth, and it is also very expensive. So that combination of makes it worth it to go to the moon and actually bring it back for sale on Earth.
It's quite expensive. How much?
$20 million per kilogram. And we know that because we've sold quite a bit of it. Now we have to go get it. But that is the price. That is also the prevailing price for what the quantities you can get from Earth sources, which are very rare.
How come that is so expensive?
Well, number one, it's in high demand. So when you have high demand, you have high price, and it is in low supply. So supply and demand drives that up. Really, most of the helium-3 on Earth today comes from the decay of tritium. Tritium is a radioactive isotope of hydrogen that is used in nuclear weapons predominantly. And it decays over a 12.3-year half-life into helium-3. So to keep the nuclear weapons potent, they have to get the helium-3 out of the warheads. And that is 90%. It's about that much. Most of the helium-3 sold on Earth comes from that nuclear weapons stockpile. And luckily, no one's really making more nuclear weapons. They're just maintaining the current stockpile. And so that supply is very limited.
How you are going to bring back the helium-3 to the Earth?
Well, we are inventing the techniques at Interlune to do that. If you had asked me or anyone, 3 or 4 years ago how they would do it, no one could really give you a clear idea. And really, when we started Interlune, we did not have a clear idea either. So that is what we're working on. I can give you a little bit of the details. So it is the reason there is more helium-3 on the moon is because it comes from the solar wind. It comes from fusion reactions in the sun. And so helium-3 and regular helium as well, helium-4, is being blasted into space by the sun in all directions. It never makes it to the surface of the Earth because the magnetosphere, the magnetic field of the Earth, pushes those ions away, and so it can't get to the surface. But the moon doesn't have a very strong magnetic field. So for billions of years, it's just been accumulating on the surface. About 1 million tons of helium-3 is what's estimated on the Earth. So think about that, 1 million tons, and it sells for $20 million per kilogram. So $20 billion a ton, and there's 1 million tons. So how do we get it back? So even though it's present, it's still not a huge amount of the soil, but it is also very loosely held, because that's the thing about helium. It doesn't react with anything. So it is just on the surface of the particles on the moon and very lightly held. So the techniques that we are developing are to excavate a large amount of lunar soil, also something that's never been done before. We have to design special machines to do it. And then there's the process of mechanically sifting and crushing it will liberate the helium gas, because you don't need to heat it. It's just on the surface of the particles. And then when you have the helium gas, a little bit is helium-3, most of it is helium-4, regular helium that you can buy on Earth. And that makes no sense to bring back. So we also need to separate the helium-3 out of the helium-4 and capture it in a bottle and then send it back with a rocket in a small capsule.
It sounds like a much tougher task than the designing a rocket ship.
It's a different kind of task. I think the thing that is different about it, that the true challenging thing about it, is because most of these processes are not hard. Large-scale excavation or even separating isotopes isn't hard. It's doing it in that extreme environment, and then doing it for the very first time in a place, in a way that it's very difficult to test. I mean, on rockets, you can test them on the ground. You can fly them every day to test them. You do not have that many opportunities to go to the moon yet to try things out.
How many opportunities you will have, or you think you will have?
We are planning a set of missions of increasing complexity. The first one is actually launching in the middle of next year, and that is to test a method for sensing helium-3, how much is present on the surface. That is our first one. We are going on a rover, as our sensor is on a rover that is not the main payload, but it is sharing a ride. And then our plan is about 3 years after that, about 3 years from now, we will send another mission called Prospect Moon, a prospecting mission, which will test for the first time our technique for cracking the helium-3 out of the soil out of the regolith.
Okay, so we are not talking about the quite distant future, but quite near future.
Quite near future, but in increasing complexity. This first mission that we're flying next year the sensor is small. It's a special multispectral camera. And then the next mission, the payload is also relatively small. It's around 50 kilograms, but it is enough for us to bring and actually test the basic technique. And then from there, we will grow into larger and larger and larger missions. And this is how, if you're trying to do something for the first time that no one has done before, you start small and you get more complicated as you pass each milestone.
Helium is your only interest in there, or?
It's our initial interest. It's our go-to-market. And in the process, actually, of getting helium-3, we also get hydrogen, which is useful not to bring back to Earth, but if somebody wants to buy it for use there, it will be available. So the reason we're starting with helium-3 is because we have customers today that want it. If we were to get hydrogen from the moon, and there's a lot of oxygen on the moon, there's a lot of water on the moon, no one will buy it right now. Even if we had it available, there's no one to sell it to. But someday there will be. When there are lunar bases, when there are more rockets going to the moon, and now they want to refuel there, these resources become very valuable. So our plan is to start with helium-3 until the lunar economy, the rest of it, starts to catch up. And then we will have a market for those other resources to the other companies that are operating there. You can also do many other things on the moon in the future, which is our business plan, but you can make solar panels out of the regolith. You can build large-scale structures. And it's much easier to get, for example, solar panels built on the moon up into Earth orbit than it is to bring it from the ground into Earth orbit.
So you think the people will live in the moon?
I think there will be some people, definitely, in my lifetime, and then growing after that will live on the moon primarily for industrial purposes. But mostly it will be robots.
Okay. Do you have some kind of robots working on?
Yes. Interlune, our entire operation, we are planning to be autonomous, so robotic. It doesn't necessarily mean, it's only 1 second of communication away from Earth, so it can be teleoperated remotely most of the time. But we have no plan to put people on the moon in order to get helium-3 back.
And you are away from the Getaway project, which is making the moon more accessible. You are by your own.
The Artemis, yes. So most of the international interest in the moon is at the South Pole. The Artemis program, as well as the Chinese international lunar bases, are both planning to operate from the South Pole. For various reasons, it's believed there are water resources in permanently shadowed craters there, but also you get a lot more sunlight most of the year at the South Pole because as the moon rotates and revolves around the Earth at the poles, the sun stays very low on the horizon most of the time. So you have very short nights and long days. Unfortunately, there is not a lot of helium-3 at the South Pole. It's not concentrated over the entire moon. There are areas of high concentration and low concentration, and most of the helium-3 is at the equator of the moon on the near side, the side that we can see. And so we need to go there. And at least initially, we don't expect anybody else to.
Is there any law, or it's like first come, first serve?
Well, there is international law and treaty. And international law works very differently than national law. International law is about cooperation between nations. And if you get enough nations that come to some agreement, it suddenly becomes international law. So there is a treaty signed by most nations called the Outer Space Treaty in 1967 that specified that nobody can own a body off of Earth and that any space activities need to be peaceful. but it was very quiet on the use of resources. So recently there has been a push to create what are called the Artemis Accords, which was pushed initially by the U.S. government. And now many countries, I believe almost 60 or more countries, have now signed the Artemis Accords. The Czech Republic is actually a signatory. And the Artemis Accords state very clearly that although you cannot claim sovereignty, you cannot own the moon or any asteroids or any of those bodies, that if you can extract resources from them, you can use them for commercial purposes. It's very clear on that. So now, because of the Artemis Accords, which includes many countries, almost all the spacefaring nations, have agreed that extraction of resources for commercial use is allowed, as long as you cannot, in the process, exclude other people from doing the same thing.
So we shouldn't expect like some kind of intergalactic war about resources.
No, that part, everything about what we're doing might sound like science fiction. The only real science fiction is the space war.
What science fiction, by the way, you read? What's your favorite author or a favorite book?
I tend to like the science fiction that is very much based on science fact. So hard for me to think of a specific one, but I do very much like the Expanse novels, and which are set in the near future. And some of it is a little bit science fiction, meaning it's not based on real physics, but for the most part, it is accurate.
And movie? Favorite?
I mean, I was inspired very much by 2001, 2010. I would say that was my favorite science fiction movies. Not so much Star Wars, not so much Star Trek. Again, I'm much more inspired by the things that if they feel like they could really happen. And that's what inspires me in my work as well.
Are you ready to fail in that process of getting to the moon and get the resources you want back?
We are planning to succeed. But we are ready for setbacks. What we are trying to do is very ambitious. It's very hard. It requires a lot of invention. So when you are faced with this project that seems like it's impossible because it's so hard and daunting, what you need to do is, and they did this on New Shepard as well, and every organization that does very ambitious things does this. They start out with the end goal in mind. And then they break that goal into a lot of little steps, a lot of little milestones. And although you still have that end goal in mind, and for Interlune, that end goal is bring a lot of helium-3 back from the moon and sell it to the customers, to the industries that want it. You can't just run to that goal right away. You have a series of steps. And they don't even start out with the moon. For us, we've been in existence 3 years. We have had many milestones that just require experimentation in a lab. So you break that up, and every time you take one of these little steps, you learn something that will change your plan. So we are planning to get to that end goal. Exactly how we will get there and whether we will have setbacks or how many, certainly there will be setbacks, we don't know for sure yet.
What about Mars? Are you interested in Mars as well?
Interlune is not focused on Mars at all. I think it is of interest primarily scientifically. I think it's very important that there be both a robotic and human exploration program of Mars. Whether or not it has a commercial interest, a true economic interest, I'm not so sure yet. Maybe someday.
You've been to space with the new Shepard, your project. Are you going to the moon with another one?
I don't think I'll be on the moon. And certainly for what Interlune does, I don't need to be. But maybe my children or the younger generation will go.
Mr. Gary Lai, thank you for your time, your information, and let's have success with your project.
Oh, thank you very much.